In this video lecture, I want you to show you how does policy looks like. We have been talking about policy a lot in our previous lectures, but we have never seen that how does actually policy looks like in classical reinforcement learning. And then we are going to see that when we introduce gradients, when we introduce parameterization to policy, then how does it look like. So normally when we are talking about policy, we are actually talking about a table that looks like this. So usually a policy looks like this. When we say that if I have a given state and I follow the policy for the next section, we basically means that we were, for example, in this state S1, we ask the policy that what is the best action to take from it. So the policy returns us a probability of actions that you can take action A1. There is 70% chance that you are going to take action A1, 20% chance that you are going to take action A2, and 10% chance that you are going to take action A3. Now, if you are following if you have followed the concept of exploration versus exploitation, and the factor that you have set is that 80% of time you are going to exploit and 20% time you are going to explore, then 80% of the time you are going to take the action with the highest probability, that is A1, and 20% are the chances that you are going to take either this one or this one. But you have to understand that even though the probability of an action is higher, it does not mean that we always take this particular action unless we are not exploring at all. And if we are not exploring at all, then we call that policy a greedy policy. But if we have some sort of exploration in our policy, then we call it an epsilon greedy policy, because we still 80% of time try to take the best action, but 20% of times we try to explore. So yeah, we can see that for any given state A, the probability of all of its action always add up to 1. I think that is understood, that for a given state, the sum of the probabilities of all of its action are going to add up to 1. Obviously, you cannot exceed 1 in terms of probability. So this table is essentially the representation of this policy pi. With the passage of time, these probabilities are going to change. For example, you explored action A2 and you got a higher reward than what you expected before, and you want to increase the probability of it, so you can increase the probability of it using the algorithms that we have learned. You can make this probability 0 0.5. So in order to keep the sum 1, what will this become? It will become 0 0.4. So because we explored and now we know that this action is also very good, we have rearranged our, or we have recomputed our probabilities using an algorithm. So this is how traditionally policies are represented before we introduce neural networks. So a policy that is not been that has yet not been parameterized is represented by this symbol called pi. But instead, but let's understand that if we have infinite states, then how the policy table is going to look. So if we have infinite state, then we are going to have S4, we have going to have S5, and so on. We will have infinite states on the left side. And consider, along with infinite state, we have infinite actions that we can take. So instead of only having A1, A2, A3, we have A infinite. We have a matrix of dimension infinite into infinite. And it is not uncommon. Suppose we are training an agent to drive in an environment, then the agent can be an infinite amount of state. It can be in any state, and it can take an infinite amount of actions from any given state. Maybe it can steer the wheel 0.5 degrees, or it can steer the wheel 0.55 degrees. These both of these are separate actions. And maybe it is in a one state, it is in a state where its velocity is 30, or it is in a state where its velocity is 30.5. So we can see that in when we are training an agent to drive, we can have an infinite amount of states, and corresponding to that we can have an infinite amount of actions to take. So we cannot use a table to represent that because it is going to be a matrix of infinity into infinity, and obviously we cannot compute infinity into infinity. So instead of storing these values in a table, we need something so that it can give us the probability of the next action on the fly. We should have something that if we put an action with a state s into this policy, it can give us the next action on the fly rather than finding it in a table. So what I'm trying to say is that if I try to create a table for infinite state and infinite actions, I will not be able to do so. And finding the next action for it is going to be very difficult because we would have infinite many actions along this axis, which is the horizontal axis. So yeah, we cannot store the probabilities for actions for a given state under classical reinforcement learning. If we have infinite states and infinite actions, we need something that can calculate these probabilities on the fly rather than storing it. And what do we need to calculate these values on the fly? We need to introduce a phenomena which can approximate this policy rather than storing it. So if we are able to introduce a phenomena that can approximate these probabilities, then rather than storing it, we can always calculate the values of these probabilities using that particular function that approximated this policy. What I mean by that, instead of storing this 0.7, 0.2, 0.1, that function is going to compute them on the fly. So that function must be able to reflect this policy. That function must be able to be as close to this policy as possible. It must be as similar to this policy as possible. So what can in mathematics, if you studied mathematics, when we want to approximate a function, what is the best way to do so? If we have infinite possibilities, the best way to do so is to introduce a neural network. Yes, this is where neural networks comes into play. If we want to approximate this policy pi, we are going to use a neural network to do so, because a neural network can handle infinite many states and infinite many actions. It is going to compute the probability of this action A on the fly rather than storing it. So we represent a neural network aided policy with parameter pi. So a policy that has been parameterized with a neural network is represented by pi of theta. What an ugly theta I have drawn. But a policy that is aided by a neural network is represented by pi of theta, where this theta represents the weight of that particular neural network. And this is where, my friends, neural networks, or we can say deep learnings, come into play for reinforcement learning. And this is also why do we need deep learning for reinforcement learning problems, because we cannot possibly calculate a an infinite into infinite matrix for our policy. We need something that can approximate the value of these actions on the fly rather than storing it. So I believe this preamble is going to help you understand that why do we need neural networks for reinforcement learning. And in the next video, I'm going to introduce policy gradients to you. You can take a quick sneak peek here as well, that instead of this matrix, we are going to create a policy which is aided by a neural network. Thus, it is going to be a parameterized policy. So yeah, let's meet in the next lecture.